Hello mathematicians, we're going to have a look at our other potential rule for numerical methods of integration, and that's Simpsons Rule. Now Simpsons Rule differs from the trapezoidal rule in that the curve is approximated by parabolic segments. So for anything other than straight line functions, linear functions, Simpsons Rule generally gives a better approximation of the area. And in fact, if the curve happens to be parabolic, it gives a very good approximation. Now Simpsons Rule for one application to this curve between x equals a and x equals b is given on your reference sheet as this. Now we don't have to know the derivation of this, which is just as well, it's not easy, but what it says is that if you look at the ends of the application, so the two values at the end, then it's the difference between those divided by 6, and then the function of one end, function of the other, and 4 times the function of the midpoint. So if we have a look at this curve here, which happens to be, as you can see, x minus 1 squared plus 1, if we wanted to approximate the area under this curve, remember that these are numerical approximations in most cases, then with one application, a and b are minus 1 and 2 respectively, and the midpoint is 0.5, so we need the function of minus 1, of 0.5 and of 2. So with one application we have 3 function values. Now part of the difficulty around Simpsons Rule is not so much using it, but getting your head around the language. So one application is 3 function values. Sometimes I'll call that 3 ordinates. Sometimes I will call it 2 strips because they call this strip and this strip an application. So what you might see is that if we have repeated applications, we'll always have to have an odd number of ordinates and an even number of strips for us to be able to do this. So for this particular curve, one application of Simpsons Rule gives us, and it's always worth writing the formula down, gives us the distance between 2 and minus 1, so that's 3 units over 6, function of one end, function of the other, and 4 times the function of the midpoint, which gives us 6 square units as the approximation of the area. Now, as with the trapezoidal rule, accuracy is increased by more applications. And as I said before, each application has 2 strips and 3 function values, so that one of those function values is the midpoint. And therefore, we'll always have an even number of strips. Now, let's have a look at GeoGebra to see what happens when we increase the number of strips. Because as we can see just here, 2 applications of Simpsons Rule just means that we repeat the formula twice, except the B and the A now become this, and then for our second application it's this and this. But again, this is the midpoint, so notice 1, 2, 3, 4, 5 function values, 4 strips, 2 applications. Now if we plug all those numbers in, and it does get a little bit tedious and easy to make an error, then we get 6.01 square units. Simpsons Rule example on here is just that diagram. It's not worth having a look at, so we'll go on to our next slide. So for this here, it says sketch a graph of the function. Now we should recognise that that function is going to be a semicircle, the positive semicircle, radius of 3. And when we go to evaluate that integral, giving the answer correct to 3 decimal places, then we can actually do the integral, if we like, or we can recognise that it's a semicircle and just take half the area of a circle. It's a lot quicker. So 14.137 square units. Complete the table, so putting those values of x in, we get these values of y. So these are the function values. So already you can probably see that we've got 5 function values here. You can imagine that that would be 2 applications, these 3 and then these 3. So we've got 4 strips, those distances there. So using those, find the area by both the trapezoidal rule and by Simpsons Rule. Now by the trapezoidal rule, then it's pretty straightforward. So the strip width, so the distance from, so remember that will be halfway between, so half of a strip width, sorry, not halfway between. So that means that when we look at this distance, which is 1.5, then half of that, so I don't know what happened there, that should be a 1.5, which is going to affect my answer. Then we've got function of one end, function of the other, and 2 times all of the other functions. So that's not going to be correct anymore. But pretty straightforward working that out. And then by Simpsons rule, it will be 2 applications. So I don't know what happened to my pen here. So that should be 3 on 6 there. 0 plus, so f of minus 3, 4 times the midpoint, and then 3. And then the same thing, the strip width, which is 3. Sorry, not the strip width, the application width, which is 3. On 6 outside of 3 plus 4 times that plus that. And 13.4 square units is our answer. So this one here is obviously wrong. This should be multiplied by a factor of 3 effectively, which would make it 12.3, which is much better. Now, just as we found with the trapezoidal rule, Simpsons rule may be adapted to find the approximate volume of revolution about an axis by using, again, our volumes by slicing technique, as we've seen before, and the procedure once again is exactly the same, except all function values are squared, and they're multiplied by pi to get the area of the slice. So in this sense, the technique is exactly the same as for the trapezoidal rule, or the adaptation is the same. So in this question here, we've got a region bounded by this curve and the x-axis between 1 and 3, rotated about the axis. Use Simpsons rule with 5 function values to approximate the volume of the solid which is formed. So this is our curve. Y equals 3 to the x minus 1, cuts at 1 on 3. We're going from 1 to 3. As we've got here, we want 5 function values, so these are going to be the function values. So each strip is 0.5, each application, so this is the b minus a part, is going to be 1. So we then simply set up our formula. So we've got pi outside of b minus a on 6, function of 1 squared. So notice it's only a little point, but that's not function of 1 squared. It's function of 1, then the whole thing is squared. 4 times the function of 1.5 squared, plus the function of 2, etc. When we evaluate those, so this is a little bit tedious once again, so we put these values, the 1 into here for example, so it becomes 3 to the 1 minus 1, which is 3 to the 0, which we're going to square. We do all of that, we hope that we don't make a mistake, or I hope I haven't made a mistake. Don't lose the pi, multiply through by pi on 6, and with any luck we get 110 pi on 3 cubic units. So remember again what we're doing. We're effectively rotating a little slice around the axis like that. So it's not a common question, the volume with either Simpsons or the trapezoidal rule, but it has come up, so we need to be aware of it. So these are the questions to have a go at. Now, any of you who have tutors, some of them might recommend using a table. I really don't like the table. I just think repeated application of Simpsons rule is better because it requires no more than understanding. It doesn't require that you memorize a table. But for those of you who will do it, and I know there'll be some, if you look at this here, the table will have the ends, the 1 and the 3. It will have 4 times sum of the ordinates and 2 times, so this and this turn up twice, 2 times some of the others. So there'll be a rule about numbering the ordinates, from this end to that end, numbering them according to whether you start from 0 or 1, remembering whether you've got even or odd numbers, remembering which ones you multiply by 4 and 2, and finally building up the table, by which time you've got no clue why you're doing what you're doing. So I heartily recommend repeated applications of Simpsons Rule. So, once more, before you get into those exercises, what were the big ideas that this is going to test? So, rather than me tell you, then you need to think about it. What do you absolutely have to understand, and perhaps absolutely have to have committed to memory, for you to successfully cope with anything they throw at you with Simpsons Rule?